Herkese merhaba. Konuşmama geldiğiniz için çok teşekkür ederim. Benim adım Derviş. Benim konuşmayı bugün İngilizce sunacağım ben size. Ben Norveç'ten geldim. Norveç'te doğdum, büyüdüm ve Türkçemi geç geliştirdim. Onun için İngilizce. Sonra isterseniz Türkçe konuşabilirsiniz benimle. So that was my short Turkish intro. My name is Dervish, and I work for the Norwegian government. I am the leader of the Norwegian Java user group, and I do a lot of voluntary work as well. So I'm involved with the community. So today I want to talk about how is actually Java changing. And there is visible changes coming to the language, which I'm very excited about. So I will just start with a brief summary. First of all, Java is about clear and readable and reliable code. Writing as less code as possible in Java has actually it's not been a goal to design the language like that. And as Brian Getz puts it, make it easier to build and maintain reliable code. That's why people continue to use and trust Java. And at the same time, I see that Java is adopting concepts well known from functional languages like record seal types, switch expressions, pattern matching, and so on. And we also have now deconstructional pattern matching much in the same way as I have learned it in Haskell. And there is more interesting things happening with Java now in the future versions of Java, such as derived record creation, value classes, and I have also seen discussions going about null-restricted value class types. I would just mention some important differences between Java as a hybrid, object-oriented functional language and a purely functional language. So first of all, maybe the first thing that you have to get used to in your head is that in a purely functional language, everything is functions. There is actually, it's everything that you define, that you declare, everything is going to be functions. And the second thing is that Java doesn't have lazy evaluation in immutability out of the box. In Java, we have the streams API and the stream pipeline, which is lazy, but otherwise it's not built into the language. And lazy evaluation, meaning expression evaluation is delayed, and it's only until the value is needed that that the evaluation will occur. Immutability is once an expression has been evaluated and an expression has a value, that value will never change, and the value will be same throughout the program's lifetime and the program's, and you can change wherever the function is used with the value of that expression. So let's take a look at the changes in Java throughout the years. I will just mention this one first, Java generics. In Java 5, we got generics. And before Java 5 and generics, the only way we could actually define a container for values was with arrays. And arrays meaning it's a covariant type. With generics, we can create generic containers of any of Java's types, as you see here. And there is actually something I noticed that I tested, and it's worth mentioning. If you have a vehicle array, and the right side of it is defined as a bus, you can actually assign a different value than the actual type of the array. And this code actually compiles, and it's only when this particular piece of code is executed, this code will fail. So it sneaks in the compilation period, and it will blow up when it's executed. So this is quite interesting thing. But with generics, This actually doesn't work, and you can only assign the same type to the list as the actual type. Then we have the diamond operator. You see that operator there, over there. It meaning that you don't need to repeat the same on the right side, and meaning that it allows a better type inference on generic types. And then on Java 10, we have the var keyword, which allows type inference on local variables. This is an example here, basically defining an array list of objects. But there is another thing that I discovered, which I didn't know about myself, and it's something called intersection types. And with the var keyword, we can actually define, let's assume that we have two interfaces. And I got this example from the Java Almanac, by the way, the link is down there. And let's say with two interfaces, they have a welcome and goodbye functions. Then what we can do is actually this. We can define a local variable, and we can define an intersection type which combines those two interfaces and providing the methods within those to the intersection type here. And the output of that code would be the one you see on the screen here. But perhaps the most important thing that happened was the streams API and the function, Java util function API introduced in Java 8 in 2014. That's basically exactly 10 years ago. And we got functional interfaces. These are some of them. And this is how it actually looks in the bytecode here. When you define a function, here I have a function that basically takes a number and outputs a number. And if we look at the compiler, we can look at this first one here, and we see that it has actually rewritten this function into a static method that takes in that the single parameter here. While the by function here, which takes two inputs, we can see that it has done the same thing except for having two parameters in. So this is what happens in the bytecode. And there are some issues because the algebraic data types has not been a part of Java. The Java util function the API and the library was built 10 years ago, long before pattern matching capabilities that we have today. There is also certain interfaces that don't build on each other, like function and bifunction. They are separate, they don't build upon each other. And the last thing here is that the streams pipeline lacks more intermediate functions and extension points. The only extension point we had to the streams pipeline is to build custom collectors. So that was 10-year data types. This is a very fundamental thing, part of a functional language. And we can divide this in two groups, sum types and product types. Sum types being that a type can be either this or that. Product types meaning it's a product of multiple parameters like Java's records, Haskell's data record types, Java classes, and so on. On the sum type, the example here is the enums, Java's enums. And together, when we have sealed classes and interfaces and records, we enable exhaustive pattern matching, and we enable destructuring and decomposition on pattern matching on the records. Before I show those examples, I just want to show you how it looks in Haskell. In Haskell, we have, for instance, an animal type. It has three constructors separated with the pipe, meaning that animal can be one of those three only, one of those. On the second line there, we see another version with the same data type, but except the data constructors have one additional constructor parameter. And then you see the functions is using pattern matching, and its pattern matches on that data constructor. But we can do much more advanced stuff with Haskell, of course, because in Haskell's data types can use different number of constructor parameters on each data type constructor there. So, and also the functions can pattern match exactly on the parameters that you are interested in, and you can skip everything else with the underscore. And we also have one data type over there called unknown. This is called the nullary type. And Haskell has also records. And records in Haskell is, as you see here, you can define a data type, and you can tell the data type what type of data it has. It has string, int, and a group. And the result of defining it like this is that you get accessor functions, as you see here. And also, algebraic data types are patterns. It represents different variants of data. And the way to think about this is, for example, a function can return an error or a result. A coordinate can have a latitude and a longitude. A chess piece can be one of several, but only one. A function might return a result or maybe nothing. In Haskell, these different types are implemented with the monadic types, and these are some of them. In Haskell, these monadic types are built into the language, so you don't need to construct these on your own. But we don't have them in Java. But with sealed types and records, we can simulate, underlining simulate, because this is not a full monadic implementation. But it's a way to demonstrate, it demonstrates how to use sealed interfaces together with record types. And also, if you look down here, you see how I can pattern match with a switch expression on the data types themselves here. So records in Java, on the other hand, they are immutable data classes with named accessors, and I usually say they are shallowly immutable because there is ways to cheat here, but generally it's immutable. In Java, we define it like this, and Java will automatically create the same accessor functions with the same name as you see here. And if we take a look at this one also in the compiler, we see that if we start with the enum, you see that the enum here, I'm sorry about the small text, by the way. You see that it's rewritten the enum to a final class that extends enum. And the record, on the other hand, this one is final class, as you see here, with the final fields. So you can be sure that it's immutable. The fields that it contains is immutable. Oh, and you also get automatically you get toString hash code equals and the accessor functions down here. And sealed types, this is one way to do it. You basically define everything individually. You add permits, and you add which actual classes can implement this interface. Here I defined the cat and dog. And the thing here is that only those two classes can implement this interface now. This is another way to do it, except I brought in the record types inside the sealed interface, which means then I don't add the permits clause here. And then we have sealed classes. And sealed classes here, as you see it, is sealed abstract class. But the same applies to sealed classes as sealed interfaces. So you declare the classes that's going to extend the sealed class, you define them as final. And the good thing about this is you can get actually the exhaustiveness. So when you have an interface that is sealed, here I have an example. I purposely didn't add the pattern matching on dog. And this code is not going to compile. And the editor, your code editor, is also going to warn you that the switch expression doesn't cover all possibilities here, which means that you can write code that is more predictive and hopefully with less bugs. But the switch expression itself has evolved. This is the way it was done before JDK 19. You can see this case matching here. It has something called guards. And the guard has a condition here. But this way of writing the guards actually disappeared once Java 19 was released, and it was replaced with when, as you see here. So this is how we do it now. And in Java 21, we got the var and deconstructional pattern matching, as you see here, because we deconstruct the record itself to extract the constructor parameters of that record. And then take a look at how this is. And you remember the Haskell version? I mean, it reminds quite much because you can, those parameters that you are not interested in, you can just skip them. And you can target only the ones you are interested in, or none of them, as you see here. And this is called unnamed patterns and variables. And again, this is an example of how I have used all of those concepts to try to resemble a monadic type called either. And it's only for demonstration purposes. It's not monadic, but it's using those monadic types in your code can make your code more expressive. Not necessarily better, but more expressive. So I want to read more, tell you more about terminology in functional programming here. And I am reading a book called the Haskell book. And in that book it says, a function is a relation between a set of possible inputs and a possible set of outputs. And it's the function itself that represents that relation between them. But I have been asking myself, what really is functional programming? Because I don't feel I understand this yet. Okay, I play with streams. Okay, I play with the Java util functions, but I don't really actually know and understand what it is. So I have been reading another book, and I have come over the stuff like composition of functions, pure functions, referential transparency, and the one I like the most, equational reasoning, and absence of side effects. And then I want to talk about that last point here, abstraction. Because what is abstraction? Abstraction is when you observe some structure or some data or something, and you start filtering relevant information for you, and you take that the data that you are observing or working on, and you present it in a simpler interface that it's easier to use. So abstraction in this context can be thought of representing patterns, structures, properties, or behaviors, and trying to make that more easily applicable. And an example of this is, for example, I took this from Wikipedia. You have an abstraction called publication, but that can be a newspaper. But a newspaper can be the Norwegian newspaper called Aftenposten. And if a more specific variant of this is, again, today's Aftenposten. So you can say that today's Aftenposten is a publication. But there is also, even though higher abstraction can make your code more expressive and less verbose, there is also called the law of leaky abstractions that you need to be careful about. Because if you abstract something and make it easy to represent, if you don't implement stuff like error handling good enough, and those and the underlying issues starting to be visible on the surface, you will have what is called leaky abstractions. And it's also that like higher level of abstraction is not necessarily better for your colleagues that is going to read your code, because I had colleagues that wrote extremely abstract code which I don't understand anything of. And in lambda calculus, abstractions is represented by lambda expressions, which you see here. Here I have three different The two first ones, they are using only their own input that is coming from only their own, the head of the lambda expression here. The other one, the last one here, is it's using a free variable from its immediate outer context here. And if you have ever heard this expression closure, it's because that inner lambda expression closes over the variable from its immediate outside context here, which then in the end can be thought of as a closed expression. So here's another example in Haskell. On the first line, I would like to filter out even numbers, and I am telling Haskell what to do and how to do it. So there's moving parts, and I have full control of everything that goes on. I'm telling how to do it and what to do. But if you want to abstract and generalize this, I would have written it with more idiomatic Haskell, where you replace this the first line with the built-in functions in Haskell, filter and even. So you have filter even numbers. Here's the equaling Java version, and this is written in imperative style. It has a for loop, if statement. I even mutate a list in here. And how would we refactor this piece of code? Well, one way to do it is to use the stream pipeline and filter, and you have the anonymous lambda expression in there. And in the end, you return the list. This one single line instead of this, and you might reduce a bunch of problems in your code. Here is a bit more difficult version. It has a for loop. It has a null. I initiated nulls here. I have if statement on multiple places. And this particular code here can also be refactored into the stream pipeline. And you can write it in a much more, in a way where you can chain the operations in the stream pipeline. So expressions, what are expressions? Expressions is values. It is variables, combination of values and expressions. And exactly like it's in mathematics, expressions have to result in a value. If you give one particular input to an expression, to a function, it has to give the same output. And which leads me over to purity. What is purity? Pure functions are referentially transparent, meaning that given an input, you always get the same output, so you can replace the function with its value wherever it's used. But there is an important thing here, because purity also means no side effects. It also means no mutation of externally visible data, which I learned from you, Venkat, thank you. And the function on the left here is pure because for each input, it returns the same output there, while the one on the right side there is not pure because it returns different values to the same piece of input. So knowing this, continuing to combining functions, and to combine functions in Java, there is 4 things that I wanted to share with you: currying, partial application, higher order functions, and composition. So curried functions basically means you have a function with a certain number of arguments. You can convert that function into multiple function with only one parameter each. So here I have a sum. It's in terms of Haskell, it would mean that it takes in a tuple, and you can add those 2 numbers and return it. But if you were to curry that function, you would say that it actually consists of 2 functions. Because we had 2 inputs on the first, that means we have 2 functions. It's constructed by 2 functions. So it takes one function with the x and returns another function out that takes y, and it can be used to multiply those numbers. So it's also higher order functions being used here. This is Java, and the reason the font is small, because the verbosity in Java makes code like super long. To represent currying, I extended a function, a function type with another function type, and you can write. This is one way of writing it. The line you should look at is down there. You apply first the first input and then the second input. You don't apply them together. You apply them to each separate function. And partially applied functions are basically when you only apply just some of the parameters that a function can accept. So here's an example. We have a multiplication operation, and I can partially apply the num function 0.66 here, and I can then use because I wanted to calculate two-thirds of a number. That's what I wanted to do, and being able to multiply that number with another number. And the calc method down there finally sets the last variable, and that you can then use it in any function that you want here. The Java version, it's, the more I look at this, the more cognitive load I feel. And even though it's possible, I hope there will be some improvements to Java that will make it easier for me to read. But to avoid this very long definitions here, I introduced a new interface, extending that interface, and then using it down here. The problem being, you have another interface to maintain. So higher order functions takes other functions as parameters or returns other functions. These are two examples. The first one takes a function in. The other one takes a function in and returns another function. So it both takes and returns. Composition. Composition, basically mapping the output from one function to the input of another function, and thus creating a new function. So here I have sort and reverse. You can basically take a list of numbers and sort them and then reverse it. This is a coding kata, the practice code I found on LeetCode, which is a website. The point here is to take an array of numbers, combine them together in such a way that when concatenated together will give you the highest possible number out of that list of numbers. And you can see in Haskell the composition of functions is being possible with that dot in the middle here that composes multiple smaller functions together. And I want you to notice one thing here. In Haskell, there is something called point-free declaration. You see that there is no input parameter here. So in a way, it's partially applied because there is no input. It's implicit that there is an input to this function. And you can use this function like this, even though you didn't specify the input parameter by itself here. Here is another Java example, and I have been scratching my head a lot because of this. I have three functions, and I have a function called class names, make, and toString. The functions basically operate on a list of data, and it returns a list of strings. And I have been trying to read in what order is those functions actually applied. And again, this thing with the cognitive load, because when I read this, you apply bus first to the make function, which does something, and the output from the make function goes to the class name function, which in the end is sent to the toString function. So you basically jump back and forth in your head like this. And I have been really scratching my head on this and hope that function composition will be much easier in the future. And then we have morphism. Why do I talk about morphism? Because while I'm reading those books about functional programming now, the longer I read into the book, there is terms and expressions and ideas that at one point or another you have to read and learn them. And morphism is one of them. Morph, it means shapes, so you basically transform shapes. And it's a term referring to transformation between objects and structures. And why do I talk about this? Because I have seen transformations and operations that are applied to data structures can actually affect logical consistency and how actually functions behave. You will need to learn what data types are better to represent and which operations are correct to use on a data in the way it's intended. So you can basically think that summing two numbers, a binary operation, is not the same as concatenating two string numbers. And I have, finally, some people, they just like to brag about very difficult words, like morphism. And at one point, you know, you had to learn it by yourself. Polymorphism is the more known one, the most fundamental principle in object-oriented programming. Here I have a function that is polymorphic because it can accept and it works on animal type and all subtypes of animal. But there's other types of morphisms. You have monomorphism. Here I have, it's basically a function that only works on its own type. So it takes a cat, it returns a cat. Takes a dog, and it returns a dog. While here, this is not monomorphic. And homeomorphism, this is the most difficult one, probably these days when I'm reading. And I spent a lot of time trying to understand this. But a function is homomorphic if it preserves structure when mapping. And what is that meaning? It means that if you have a data type, here I have price. I wanted to model the increase in price, which is, there's a Turkish word, zam. So I wanted to model that one because I feel it's appropriate the time we are doing it. And there is a multiplication operation applied to this data structure that you see here. So if you follow the composition law, you can see that sum of 50 equals sum of 25 plus sum of 25. Because the composition law applies and the multiplication operation, the way it's implemented here, preserves that structure on the multiplication. Here, however, I changed the data type to string. And the problem here now is, even though it multiplies correct on the first line, when you actually follow the composition law, it will not do binary operation, it will do string concatenation. So this is not homomorphic. So if you were to have a data structure and you accidentally used some wrong data type and in that way misinterpreted the way the data is supposed to be used, then it can lead to problems. And if you have two data types and there is a bridge between them without the loss of information, then those functions will be what is called isomorphic to each other. And this is, here I have a point and I have a tuple, and there is a way between both of them, and you don't have a loss of information here. It's only the data contained in both of them is transferred back and forth. So that is then, you say that those two functions are isomorphic. And data modeling. When I was doing Java in the object-oriented with the classes, and when I started looking at Haskell and I have only functions, and I'm thinking, okay, how do I deal with the state, and how do I deal with the file reading input and a lot of stuff? How do I do this when I only have functions? So you have to basically think very differently when you do functional programming. And I can tell you from my own experience, this is actually not easy. It takes time, and you need this change in your mindset. But I would explain as you need to separate the data represented by values and operations on those data through your functions. So you describe your data first, you describe your values through your data, and then you describe the operations that will work on those values through your functions. So in Java, in object-oriented version of the classes, you would encapsulate the data and the operations on data inside this class. In a functional way, you would have to divide those because we have only functions. So you have the data types, the model, and then you declare the functions that will operate on those data. Here is, for example, the fold function, which I have defined here. You see that the function declaration is on the first line. In the function declaration is saying to you, what do I want to achieve? What do I want to solve here? Well, I want to take a list of salary, and I want to transform it into a salary data object. And this is being Haskell. You have a list comprehension in here to sum up the amount of each value, and then you do some operation, and you return the total sum in that object, which is called data salary. And this is pure, and it's immutable. But it's not homeomorphic. It's not homeomorphic because of the way the average is being calculated here. Because when you divide two structures into its two different parts and then putting it together, the average calculation will be wrong. But it's pure and it's immutable. In Java, we would represent the data types in Haskell with records, and the operations with functions like this. And again, as I said, there is a big issue with sentences tend to be very, very long in Java. So again, I tried to introduce this extra interface. So this is the way I ended up doing. Well, you have an extra interface to care about now. So in the end, I ended up with something like this, because I wanted the code example to be pure, as much purely functional as possible. No side effects, immutable structures. And I came up with, here's my model, and here is the pure functions. And they are pure because they only operate on its own input there. And but there is something that happened, because when I was trying those simple examples, that was good. I was inspired. I have to do this more. And then came at one point when I wanted to test those ideas. And I said to myself, what if I could make a game? And there is something called Pirates, Liars, Dice. So I wanted to implement. It's basically two players rolling a dice, and they sum up the value, and they bid against each other, and they would sum up the highest possible number out of those dices. And I was thinking, okay, so first of all, I learned about monads, even though it's not exactly the 100% implemented. I simulated it. It reads in data from a API, external API, and it's putting it that the operation will happen only within this monad there. So it started fine. Functions are small. I had a lot of fun. Stuff seemed to work. And then as I implement more and more of the rules of the game, then I noticed some things started happening, because I started losing actually the overview of what was going on. And when I came down here, when I look at this code now, I'm still asking, what was I thinking? And what exactly goes on here? Because I have this, for example, this one. I'm composing functions, that's fine. But what exactly goes on here? If you had never seen this code, I mean, if my colleagues had never seen this code, they will beat me now. And it continues like this, and it's possible. This is what I wanted to prove. Is it actually possible to do as pure as possible? But it's actually really hard. there is some advantages. There is, you can benefit from the functional style, the expressive style of working with this kind of working with Java. You can implement algebraic data types, pattern match on those, decompose them. You can avoid side effects and shared visible mutability. Immutable data as much as possible. Pure functions and no nulls through those monadic types. But be aware of one thing. There is pitfalls, such as parallelism. And then there's what are the actual issues going pure functional in a language that is not meant to be like that. First of all, it takes a lot of time to learn functional programming and functional style of. So you have to invest time. It's not impossible. You have to invest time. And then Java is really, really verbose. Lazy and immutability is not out of the box. Composition is hard and verbose. But maybe probably the two things that bothers me the most is, first of all, weaker type inference compared to language such as Haskell. And it's harder to actually model and deal with side effects in a pure style. Because if you want to deal with side effects in a pure style, you need to learn how to operate with monads, which is how Haskell solves it. And that takes time as well. So what did I learn? It's important to clearly declare functions. You have to tell what you want to solve, not how you want to solve it. You compose several small functions into bigger ones, and you contain and you handle side effects within data structures such as monads, pattern matching, algebraic data types, and creating immutable structures and combining the streams, the functional style, with the function, the Java util function API. So because neither one of them is better than one of them. I mean, you try to use the right tool for the right job. But I think today that combining ideas from a purely functional language, learning those ideas and applying it to my own work wherever I can, it's contributing to make my code better than it used to be. And so it can have its advantages, but it has to be used wisely because you can end up introducing much more bugs than you are actually hoping to solve by trying to replicate something that is built into a language like Haskell. So the journey that I have been walking through here is that you need to embrace functions and functions as a natural part of the language. And you need to, you will need to relearn a lot of things. You will need to revisit, for example, what is object orientation? You need to revisit this. You need to look at mathematical concepts from category theory. This is not what you start with, but at one point in time, when you went a little bit further, those you will need to understand them to benefit much more. And then it's the questions, many questions. State, I/O, how do I iterate over data? Well, in Haskell, you have already higher order functions to do this for you. But when you are going to do it yourself, you need to change your complete mindset. So I hope that was inspiring to you. I hope that contributed something to you. And if you have any questions, I will be standing here and I will be outside. So please ask me whatever in either Turkish or in English, whatever you prefer. So I will be here. So thank you so much.